Hey class, I appreciate y'all being understanding the death of my brother, and I did have to reschedule some things, but I'm finally getting around to the review for test 3, and I will open up test 3. It's actually Monday morning at 4 a.m. And so I will be opening up test 3 probably today. So hopefully you'll watch the review. I did have the extra credit quiz out there. And I'll give you plenty of time to work on the test. So you might want to wait and start it, oh, I don't know, Tuesday or something after you have had a chance to watch the video and do the extra credit quiz. So this is just what it's going to be over: the polynomial functions and equations, functions with radicals, and the functions with rational exponents. Rational functions, rational equations, polynomial and rational inequalities. And unfortunately, I didn't get to this yet. I will shortly, hopefully today, but it will not be on this test. So the polynomial functions, and it was these two sections. For example, say we had this function, and you have a question, something like this, where you have to determine all of these things, A through E. So one of the things that you'll have to determine is the end behavior. And if you remember, when you've got a function like this, I'm gonna move this down just a little bit so I can see it. You can see it pretty well there. Make sure it's not. There we go. So this is what this equation or this function looks like. So remember, to determine the end behavior, you need the leading term. And when it's in the factor form, like it's in right now, you need to find the leading term. You can't just read it off. Hold on just a minute. Let me move this. That thing's oriented a little bit differently this time. So what you want to do is you want to take the leading term from each factor and raise it to whatever the exponent is. In these factors, the exponent is 1. So what I'm going to get is an x squared times an x times an x, which is going to give me x to the 4th. Okay, so, and if I had a constant out here, like a 2 or a -1 or whatever, that would also be multiplied times the leading term. So this term determines the end behavior, and it really determines a lot about how the function is going to look. So, and when we're talking about end behavior, a lot of times we're talking about graphing, not always, but a lot of times we're talking about graphing. So if you remember, there are 4 cases for the end behavior. So for the end behavior, if the leading term is, let's say, even, and so let's call the leading term with the coefficient, and then it'll have an x to some number. The number up here is the degree, so that's the degree. Now, if the degree is even, then there's 2 cases. If the leading coefficient is positive, then both ends are going to open up. If the leading coefficient is negative, both ends are going to open down like that. So another way to say this is, as n goes to infinity, your function, or actually I should say it's n, I'm sorry, I'm tired here. As x goes to infinity, f of x goes to infinity. And remember, and I've already taught y'all this, as x goes to negative infinity, your f of x is going to infinity. So I'm not going to reteach the whole thing, but remember how that goes. Now, this is if the leading coefficient is negative. And then there's also the 2 possibilities for the degree being odd. Remember, one end's going to go down and one end's going to go up. or it's going to go like this. And it depends on, it's like this if the leading coefficient's positive, and it's like this if the leading coefficient's negative. So anyways, when we look at this particular problem, my leading term is this x to the fourth. So my leading coefficient is just 1, which is positive, and then 4 is the degree. Which is even. So that means that the ends are going to go up like this. Now, what the question says over here, the graph of f behaves like y equal, and that would be this x to the fourth that would go here. So what that means is by the end behavior that if x is either going to infinity or negative infinity, that's what this means for large values of absolute value of x. That means as x goes to infinity or as x goes to negative infinity. So we're talking about the end behavior here. Then the function is going to behave like x to the fourth. And that's what we're talking about. End behavior, well, right there, it didn't really ask. It might ask like for you to choose which end behavior it has. So what you would have to say for the end behavior in this case is, or what you would have to choose if it's listed like this, as x goes to infinity, your f of x or your y goes to infinity, and also as x goes to negative infinity, the y goes to infinity. So it's opening up like that. That's one thing we know about this function. Okay, find the x and y intercepts of the function. And since this function is already in factored form, it's pretty easy to see what the x and y intercepts are. And you can see that they're x equals 0, x equal plus or minus 4. And you've already learned how to find x and y intercepts. The y intercept is going to be y equals 0, because if we put 0 in for x, we're going to get 0 for y. And then determine the zeros of the function and their multiplicity, and determine whether the graph crosses or touches the x-axis at each x-intercept. Well, remember that the zeros are just the like I was saying, the zeros are just the x-intercepts. So we've got x equals 0, x equal 4, and x equal negative 4. And here's the function. The multiplicity for x equals 0 is a 2. And what we're interested in here is whether it is even or odd. And what the multiplicity, where that comes from, is the exponent right here. So the multiplicity is 2, so that means it's going to touch the x-axis and turn around. Now over here at 4 and negative 4, the multiplicity is 1. So the multiplicity equals 1, and that's an odd number. That means it's going to cross the x-axis. Okay, so you would fill in, and it wants you to fill it in with the smallest one first. So always be sure you do that correctly. And then it just asks you what the 0 is, what the multiplicity is, and then you'll have a choice of whether it crosses the x-axis or touches and turns around. Now, the maximum number of turning points is the degree minus 1. And remember, the turning points are just where the graph changes from increasing to decreasing, or from decreasing to increasing. And so it's going to be degree minus 1. In this case, the degree is 4. So it's 4 minus 1, which is 3. And let's see. And then it says to use the above information to draw a graph of the function, and you'll have to choose the correct graph. But you know, back from when we had to graph by hand, back in the olden days, we know some things. We know it opens up at the ends. We know at -4 it's going to cross, and that at +4 it's going to cross. And we know it's going to have to go down and come back up. We don't know how far down it's going to go, but we know it's going to go down and come back up. And at 0, at that 0, x equals 0, it's just going to touch and turn. So we kind of know that it's going to look like this. Now, I also graphed it on my calculator because we can do that now. And this is what I got on my calculator. So you see that's the ends going up. This is it crossing at -4 and 4, and it touching at 0. Now, back in the olden days, we probably would have picked some value about halfway in between here, like -2 and 2, and substituted into the function to get an idea of how low it goes right here. What's the lowest y value? But that doesn't tell us exactly. And the turning point, since it was 3, well, we actually do have 3 turning points. There's one here, and one here. And we know that's the most that we're going to have. And that would help with determining the graph. So we also have equations that are quadratic in form. So for instance, this is an equation that's quadratic in form. And you see that if we get it in standard form, it is quadratic in form. It's not a quadratic, but it is quadratic in form. So it's p squared minus 13p squared plus 30. And so it's in the form, it's a 4th degree polynomial. So it's not a quadratic. Okay, but it is in the form of a quadratic. If you look at it, because p squared gets squared, and then there it is just with the p squared, and there's the constant term. So it's in the form ax squared plus bx plus c equals 0. Oops, went all the way across the page there, which is the form of a quadratic. So what we want to do is make this substitution and say, let's let u equal p squared. And we're just going to do that so that we can factor it. So then if I'm letting u, I'm going to put u where p squared is. So I have u squared minus 13u plus 30 equals 0. And then you would go ahead and you would finish factoring that. And I'll just show you where I did that. So just to save some time here, I factored it. I set it equal to 0 and use the zero product principle. I solve, and then at this point, what I did, you could do this now or you could do it later, but somewhere you've got to change the u back into p squared because we're solving for p, not u. So I just did it in the factoring step here so I wouldn't forget. And so over here, I get plus or minus the square root of 10. And over here, I get plus or minus 3. So notice I get 4 solutions, which makes sense because it was degree 4. So the degree tells us how many solutions we should be able to account for. And it may repeat the same solution, but it should, the degree tells us like how many we should be able to account for. Okay, so let's look at the next question. And I'm going to try to speed up a little bit here and go through this one without writing it all out myself. Well, let me look at it. You can't really see it right there. Let me write it out. Okay, so this is the problem. This is quadratic in form. If we let u equal whatever this middle variable is, so I'm going to let it equal square root of x, u squared would be equal to the square root of x squared, which would be x. So this actually is quadratic in form, and sometimes you see this. So this is the square root of x squared minus 4 times the square root of x minus 60 equals 0. So I'm going to, in this case, let u equal the square root of x. Okay, so it is quadratic in form, but it actually is not even a polynomial. It's a radical function. But I go ahead and I solve it. And I factor, so reverse the substitution, so put the square root back in. So this is just where I made the substitution. I put u where square root of x was, and then I factor it. And then I replace or reverse the substitution. I put square root of x back where u is. And then I have two equations to solve. They're radical equations. So remember, we square both sides. And I get x equal 100 and x equal 36. And you know, you should always check and make sure that your solutions are going to work when you're solving a radical equation. That's one of the things that you must do, because you can get extraneous solutions. And when we go back and we check in the original equation, we got two solutions here. It worked here, but it did not work here. So when we got x equals 36, that was an extraneous solution. So that's something to remember about radical equations or square root equations. You must check for extraneous solutions at the end. So whatever you get, you must go back and check. Okay. And here is a radical equation. And so remember, what we do is we square both sides. And the reason we do that is to get rid of that square root. So we square both sides. And when we square the square root, it undoes the square root, or they cancel each other out. And let's just look at what I did over here and talk about it. I won't write the whole thing again. Okay, so I squared both sides, and then I get this equation, which is a quadratic. I'm going to leave it all on this side. It's easier to factor if your leading term here, your x squared term, is positive. And so I factor it, and I get x equal minus 6 and x equal 2. So far what I've done, if you look at the steps, I isolate the radical term on one side of the equal side. I square both sides, I solve, and then I have to check. So we're in the solving process, and we get the two possible solutions. I have to check each one separately. So when I check the -8 and I put this in, square root of 64 is not -8. So that's an extraneous solution. When I check the 2 over here, it does check. So my only solution is 2. So just remember, you have to check for extraneous solutions. please remember that, okay? See what else we've got here. Okay, so we have an equation that has a fractional exponent. This is actually the same thing as if that were a square root symbol. These mean the same thing. The 1/2 power is the same thing as the square root. So we really solve it the same way. We we isolate the exponent, and I'm just showing you over here. We isolate the exponent, and then we raise to the reciprocal of the exponent. So the reciprocal of 1/2 is 2, and we need to raise both sides to that. It's very important also that you have the term raised to the exponent isolated. And I see that mistake a lot. And see, when you raise a power to a power, you multiply the exponents. So we get 8x plus 4 raised to the first power equal 36. And then I need to check. I need to solve. And then since this is like a square root, it's the same thing as a square root, we need to check it. Now, really, you only have to check it if the denominator of the fractional exponent is even, but I would just say go ahead and check them anyways instead of trying to remember that. So we go back and we check, and we get down to here, substitute in a 4, which is what I got. And then I get is 36 equal to 6 squared, and it is, so my solution then is 4. Okay. And then we talked about rational functions. Just make sure I didn't skip anything up there. All right. The things we're going to need to be able to do with rational functions: find the domain and range and the intercepts, and rational functions may have asymptotes. So you've got to remember about vertical and horizontal asymptotes. So graph a rational function using transformations. So for example, well, here we're not graphing yet. We're just going to find the domain, the vertical asymptote, and the horizontal asymptote, or asymptotes. So let's see if I can zoom in on this enough for y'all to read it. Let's see. Okay, that looks good. Well, the domain is x can't be negative 19. And so that's how you write it out in interval notation. Now, the vertical asymptote is this value that x can't be, the negative 19. So it's whatever makes the denominator equal to 0. And so that's negative 19. That's the vertical asymptote. The horizontal asymptote, if you remember, there are 3 cases with the horizontal asymptote. So remember, we take the leading terms, and if n equals m, so if the exponents are the same here, then it's going to be y equal, and it's going to be, oh, I should call this, these won't necessarily be the same number, so I should say b right here. So it will be a over b. And remember, a horizontal asymptote is a horizontal line. And so it's going to go y equal. And what a horizontal asymptote is out at the end behavior, if a function is starting to look linear like this, and say, just say for instance that this is x equals 0 or y equals 0, I'm sorry, then we say that that's the horizontal asymptote. Okay, now back to the cases. If n is greater than m, there will be no horizontal asymptote. And if n is less than m, then y equals 0 will be the horizontal asymptote. So you need to review that. Okay, so in this example, we were looking at the horizontal asymptote in this case, because the degree in the numerator is 1 and the degree in the denominator is 1. So we take the leading coefficient in the numerator divided by the leading coefficient in the denominator. So here's just where I wrote out those three cases. So the horizontal asymptote in this case is going to be y equal 8 over 1. So y equal 8. And then the range, you could graph this to see it, but what happens usually, and let's just graph it and look at it. Let me go ahead and graph it. So let's see. And when you're graphing these, be sure if your numerator or denominator has more than one term, or if the denominator is even just multiplied by some number, you need to be really careful how you enter this on your calculator. So I'll get the right one in there. Yeah, 8x over x plus 19. Be sure you put this in parentheses. Here, it's not going to matter, but if it was 8x in the denominator, you would have to put it in parentheses, because what it's going to do is it's going to divide by the first thing it sees. And so if it just sees an x, it's just going to divide by an x and then add the 19 to the whole thing. So if you wanted it to divide by two terms, you need to put them in parentheses. And then let's see what it looks like. Let's see. I'm surprised it looks like that. Let me try a different zoom. That looks more like it. So we see that it has a vertical asymptote, and you can always check these things. We said it should be at x equal negative 19. So if you do second function calc and you enter a negative 19, do we get, yes, we don't get a value for y, so it's undefined there. So we see that that is a vertical asymptote. Now the horizontal asymptote is what's happening as we're going off this way. Sometimes it might help to look at the table. So if we look at the table here and just look, it's hard to tell until x really gets big. So let's change our table setting and let's let x get big and go by hundreds just to see what's happening in our table. And then we see, and what did we say it was going to be? That it was going to be 8. We can kind of see it starting to get closer to 8 here. If you look at it, as the x is getting bigger, it is getting closer to 8. So we were talking about the range here. So let's go back. Let me go back and zoom out. See if I can see this again. So of course, well, the x value is never going to be negative 19. The y value is, it's going to keep going up, but it's going to come down towards this horizontal asymptote, but it's actually never going to get to the horizontal asymptote. So the range is going to be, I need to write that out. right here from negative infinity to 8 union with 8 to infinity. Because what it's actually doing here, if you think about it, it's got a vertical asymptote at x equal negative 19. And it looks like what it's doing here is, and this is at y equal 8. So it's doing like this over here. And then it's doing like this over here. So the y is never going to get to be 8. It skips over 8. Okay. And then let's see. Oh, we had another one, right? Well, that's all we really need. Or do we? Okay, let's look at this one. There is one more right here. So this one is x over x cubed plus 8. So if you, the degree of the numerator is 1 and the degree of the denominator is 3. So if the degree of the denominator is greater than the degree of the numerator, the horizontal asymptote is just going to be y equals 0. Now, in this case, if you set the denominator equal to 0, you'll get that the vertical asymptote is x equal negative 2. And we've got the horizontal asymptote is y equals 0. And what else were they asking for? The domain. So the domain would be x can't be negative 2. So it would be from negative infinity to negative 2 unioned with negative 2 to infinity. And then the range, since y can't be 0, it would be from negative infinity to 0 union with 0 to infinity. So that would be the range, and this would be the domain for that problem right there. Right. So there could be a problem where you're given a graph and you want to find the domain and range, the intercepts, if any, the horizontal asymptote, the vertical asymptote, and don't worry about these. So if you look at this graph, you can see that it's got a vertical asymptote. Vertical asymptote is going to be a vertical line at x equal, let's see, it looks like x equal 2. And it's got a horizontal asymptote. It looks like this line is getting closer to y equal 2. So y equal 2 is the horizontal asymptote. X equal 2. Oh, and I'm sorry, that should be a minus 2. Y equal minus 2. And below the x-axis right there. All right, so that's about minus 2, I think, is the horizontal asymptote. X equal positive 2 is the vertical asymptote. Intercepts, it looks like x equals 0 is the x-intercept, y equals 0 is the y-intercept. There aren't going to be any other intercepts because this is not going to cross over this horizontal asymptote. Now, that was all they asked for. Oh, the domain and the range. The domain, well, we can't have x equal to 2. So it's from negative infinity to 2, union with 2 to infinity. And the range, we can't have y be negative 2. Like that. Okay. And then they want to subtract a rational function. And so we want to graph it. Using transformation, use the final graph to find the domain and range, and use the final graph to list the vertical, horizontal, and don't worry about the oblique asymptotes. We don't cover that in this class. Okay, so what this function is, it's f of x equals 5 plus 4 over x plus 2 squared. So the function that is being transformed is y equal 1 over x squared. That's what we call the original function or the parent function. And what's being done to it, it's going to be shifted left 2 units and up 5 units. And also it will have a vertical stretch by 4. So it will also have a vertical stretch. By a factor of 4. Because of this 4 right here. So this is what y equal 1 over x squared kind of roughly looks like. It's not a very good picture really, but it has both pieces above the x-axis. It has a horizontal asymptote at y equal 0, and it has a vertical asymptote at x equals 0. Now, this one is going to be shifted left 2 units. So we shift over to where x equal -2, because we can see that that's where the vertical asymptote is going to be. And then the horizontal asymptote, because we're shifted up 5 units, normally the horizontal asymptote would be y equals 0, but since we're shifted up 5 units, it's going to be y equal 5. So this is y equal 5 horizontal asymptote because of that shift up, and this is x equals -2 because that shift left. And then that's what the drawing looks like, the graph. And so if you're looking for the domain of this function, we look at the vertical asymptote because that's what x can't be. So x can't be -2. And if we're looking for the range, we look at what the horizontal asymptote is, the 5. And so y can't be 5. Like that. Okay. This is just solving a rational equation. So remember, the way you do this is you factor the denominators. And that allows us to find out what the LCD is. In this case, it's x minus 7 times x plus 7. So over here, we've got an x plus 7 as the denominator. Here, we've got an x minus 7. Here, we've got the product. So if we just use this denominator here, the x plus 7 goes into this, and also the x minus 7 goes into this. So then what we need to do is we need to multiply every term by this x minus 7 times x plus 7. I'll let you do that on your own, but the answer you get should be, when you do all of that, because when we multiply by this, we're going to have some denominators, well, all the denominators are going to cancel. And we get x equal -7, but can x be -7? X can't be a -7 or 7. So this is a special thing for rational equations. We have to check that our solution does not cause 0 in the denominator. Okay, so that's a special thing that we have to do with rational equations. And let's see. Then the last thing we had were the polynomial inequalities. So the first thing you want to do is get 0 on one side, and then we're going to factor it. And we do that to find out what the zeros are, or actually what the boundary, we call them boundary numbers. So we get x equals 0 and x equals -8. So what we do is we're not, when we're doing this, we've actually changed the problem to be, I think that's a 2 right there, to be 2x squared minus or plus 16x squared equals 0. So we change to this to find the boundary numbers. And then what the boundary numbers do is they tell us what to plot on this number line. The boundary numbers are really the zeros. If you thought of this as a function, so if you think of the function, that would be f of x equals 2x cubed. That's a cube right there. I'm sorry. 2x cubed plus 16x squared. They're the zeros of this function. And depending on the multiplicity of the 0, it's either going to cross the x-axis or it's going to touch and turn around. Now, so what may happen at the boundary number is this inequality may change from being true to false or false to true. So what we do is we figure out what these boundary numbers are, and then we pick some values, not the boundary numbers themselves, but values in each of these 3 parts of the number line. So we pick one less than -8. So I picked x equals -9. I picked one in between. So between -8 and 0. So I picked x equals -1. And then a number greater than 0. So I picked x equals 1. We go and we substitute these values back into the inequality to see, and you could do it with the first inequality or the one when I get 0 on one side, which might be easier. And then I see if I get true or false. But what I get here, I get 1,458. Is that greater than -1,286? That should be, oh, no, that's, yeah, wait a minute. This should be true. Yeah, it should be true right here, sorry. I don't know why it says false. Unless I've got something, unless I'm confusing some, oh, I know what it is. It is false. That's a negative sign right there. So it is false, because that is more negative than that. So this is false. And then in here, we get a true. So this is part of the solution set. And over here, when we substitute x equal 1, we also get true. So it doesn't always go true, false, true, false. It doesn't always alternate like that. The reason it does that is because if you looked at this in factored form, like we've got it up here and we factored out an 2x squared, this is where we get the x equals 0, and it has a multiplicity of 2. So it actually, the graph doesn't cross the number line at x equals 0. It touches and turns around. So that means that it's not true at 0 because it's strictly greater than, but it is true on either side. It's true at x equal -1 and x equal 1. Now, let's see if we can get a decent graph of this, and I'll explain it using the graph. Let's see. Yeah, we can kind of see what's happening. So we're wanting to know where this is greater than 0. So it's greater than 0 when it's above the x-axis. So this is -8, so from -8 to 0. Now it's not above 0 when it touches 0, but then it is from 0 on out to infinity. And that's what we got for our solution. Okay, then we should have a rational inequality somewhere. Yep, here's one. Rational inequality is similar, but we're going to have two types of boundary numbers. So okay, this is sort of a mess. So let me do it again over here. Let's see what else I can do. This is what I was doing just a minute ago, solving just by looking at the function. If this is the function and we're wanting to know where it's less than or equal to 0, it's when it's the x values where it's below the x-axis. So it's -infinity up to -2. And then over here from, it looks like 3 to infinity. Look at that one. And then I wanted to do a rational inequality. I just didn't have a good one. Okay, so let's look at this. So we've got 1 over x minus 2 less than 2 over 3x minus 18. And so I'm going to go ahead and I'm going to factor the denominators. Factor out a 3 here. And so then what I'm going to do is I'm going to find my boundary numbers, and you can go ahead. You can get this if you want with 0 on one side. You could get a common denominator here. And I guess we should, shouldn't we? The LCD here is going to be a 3 times an x minus 2 times an x minus 6. So we're going to do that so we can find the boundary numbers. So remember, we multiply every term, and let's just go ahead and change this to an equal sign, because what we're doing here is we're going to find the boundary numbers. Okay, so I'm going to multiply every term by this. It's going to get kind of messy. Okay, I think I've got everything written out there. Okay, so what's going to cancel? The x minus 2s, the 3, and the x minus 6. And then what we've got left is a 3 times x minus 6 minus a 2 times x minus 2 equals 0. All right. And so let's see. We've got 3x minus 18 minus 2x plus 4 equals 0. So we've got a 3x minus a 2x, that's an x. And then minus 18 plus 4, that's a minus 14 equals 0. So we get x equal 14. Now that's going to be a boundary number. That is actually the that's the x-intercept or the 0. Now the other boundary number is going to be the vertical asymptote. So the other boundary numbers is, so we look back at what we had here for our inequality. We can just go back to the original inequality. And we set these denominators equal to 0. So we'll get x equal 2 as a boundary number. And that was supposed to be a 6 right here. And we'll get x equals 6 as a boundary number. Now, these are the vertical asymptotes. Now, so basically what we're saying is an inequality can change from being true to false or false to true at vertical asymptotes or at x-intercepts and or at x-intercepts. So the thing about the boundary numbers that are the vertical asymptotes, you would never include those in your solution set. So we've got all our boundary numbers. We've got 2, 6, and 14. And remember, these two are vertical asymptotes. And we would go and test. And so I did that. And I got true, false, true, false. Now, we've got to skip over the boundary numbers that were vertical asymptotes. And even if it had, normally we would include the boundary numbers if it had an equal under it, but not if those boundary numbers are x-intercepts, are vertical asymptotes. So we don't include them. So it goes like this: negative infinity to 2, because it's true there. It's false in here. So then it's true over here. So we go union with 6 to 14. And that is the solution of that rational inequality. Okay, that's it, guys. So I think I'm going to get some sleep, and I'll see y'all later. I'm going to try to get caught up. Bye-bye, guys.